What is work, energy, and power from a physics point of view? In this video, I'll show you how these things are interrelated. So first, let's talk about work. So work is simply just a force times a distance. And the usual way of describing that is, imagine we've got some box and we're going to push it. We're going to push this box across the floor. And as we push it across the floor, we're going to move it some distance, call it d. So we apply a force like this. Let's say it's 100 newtons. And we move it for some distance, and let's say that's 20 meters, like that. So that's our force, and that's our distance. So work is just going to be this force times this distance. So 100 newtons times 20 meters, like this. And so that's going to be 2,000 joules, which is a newton times a meter. So 2,000 joules, something like that. So that's what work is. How is that related to energy? Well, if we were pushing this box, and let's say that the surface was frictionless, and we pushed it for this 20-meter distance, then what would happen is this box will have picked up speed, and if there was no friction at all, it would just keep going. And it would have this speed, and it would just keep going forever and ever. So by applying work to the box, we give the box some sort of energy. It has some sort of energy. And this is energy associated with movement, and so we would call it has kinetic energy, like that. There's a way to describe how kinetic energy is related to work with a simple example. So let's say I have this apple, and I want to lift it up. So here's my apple, and I'm going to lift it up like this over some height h. That's the height of the shelf. And after I lift it up that height h, then I can place it on the top of the shelf here. Right? So I've moved it a distance, h. I've had to apply a force to it. The force I had to apply to it was at least equal to the weight of the apple, so it's mg. So I'm moving it in this direction, h, that's the distance. I'm applying a force of mg to get the apple up there. And so the work that I put in is equal to the force times the distance, like that. And the force is mg, and the distance it moves is h. So the work that I put in is m times g times h. But that's also what we would call the potential energy of this apple. Potential energy. So it's gravitational potential energy in the following sense, that if that apple's sitting up there, as long as it's sitting up there, it could be knocked off. And so if I push it and the apple falls, then when the apple's falling, it has energy that's related to motion. Again, this is kinetic energy, which we often abbreviate by Ke, like this. And you can show that the kinetic energy is basically equal to 1/2 mv squared. I showed that in class using one of the kinematic equations. So now if we go back to our understanding of things, we've got work, which is some amount of force times distance, that can create different types of energy. I can have gravitational potential energy, which is equal to mgh, or I can have kinetic energy that's equal to 1/2 mv squared. So let me just write that down. I have force times distance. This is work. Then I can have gravitational potential energy given by mgh, and sometimes we just write that as Pe. And then we can have kinetic energy, which is 1/2 mv squared, like this. And so we can write this as Ke, like this. Now, as long as there's no friction going on, the energy will be conserved. So an example I gave in class was somebody's riding around on a skateboard. And this is on one of those PhET simulations. So somebody's riding on a skateboard, and as they're going back and forth, they're going up, and then they're going back down, and they travel back and forth in this parabolic path. And what happens is that the total amount of kinetic energy plus the potential energy will remain constant. So up at the top, what will happen is the rider will get all the way up at the top, they'll slow down and they'll come to a stop. And when they come to a stop, what that means is that their kinetic energy, if I were to draw like little histogram bars here, their kinetic energy is nearly zero right at the top, but their potential energy is high. And then at the bottom, when they're down here and they're traveling, what happens is they're traveling very fast, so their kinetic energy is high and their potential energy is very low. Now, the sum of these two bars in the histogram is always going to equal a constant. But one might go higher and one might go lower depending on the position of the person as they go back and forth along this parabolic path. Kinetic energy will be highest at the bottom, and potential energy will be zero. And up at the turning points at either end of this, you will have high potential energy and zero kinetic energy, like that. So this is the conservation of energy. Conservation of energy will not apply, though, if there is friction. If there's friction, you'll have losses. And so an example of that would be something like this. Imagine we have some leaf, and this leaf is going to fall from a tree. It's going to go down, and it's going to hit the ground like this. And right before it falls off the tree, right before it falls off the branch, it has an initial velocity of 0. And at the bottom, it will have some final velocity that will not be 0. And what we could do is we could say the total energy of the leaf must be conserved. So its potential energy plus its kinetic energy initially must equal its potential energy plus its kinetic energy final, if there's no loss due to friction. But as this thing falls, it's going to have some loss due to friction. So how do we account for that? Well, let's try to look at what the potential energy is at the very top. So the potential energy is just going to be m times g times h initially, before the leaf falls. It'll have 0 kinetic energy because it has no velocity. So 1/2 mass times velocity squared. This is going to be 0. So its total energy at the top is just m times g times h. So this is the total energy at the top initially. Now down at the bottom, if we go down here, when it hits, what happens is it no longer has any height. So m times g times h. H is just 0, so that goes to nothing. And now what does it have? It has some sort of velocity going here. So it'll have some final velocity, and that'll be its only type of energy. So what we can do is we can say, we'll say that the initial energy is mgh, and then what's going to happen is that's going to all become 1/2 mv squared, like that. So I could calculate these things, and I don't know, let's say I find out that this is 0.1 joules, something like that. And let's say I find out that this is 0.05 joules. So it goes like this. So that was its initial energy up at the top, and this is its final energy, like that. You go, well, why isn't it conserved? Well, I can take the difference between these two, and I can find out that the difference basically is this missing 0.05 joules. This part right here must be due to friction. So this 0.1 joules became 0.05 joules of kinetic energy plus 0.05 joules of energy lost to friction. So as the leaf fell down, as it kind of rocked back and forth as it came to the bottom, it basically interacted with the air, and it heated up air molecules, it heated up the leaf itself, and so that energy was lost to friction. And so if we account for friction, then yes, energy is totally conserved, something like this. But if we're just looking at kinetic and potential energy, what will happen is we're going to lose some due to friction. So we've talked here about work and energy, and now the last thing that I want to mention is power. What is power? So power is just the rate at which work is done. So power is basically equal to work or energy divided by time, like that. So for example, I could say we've done 10 joules of work on something in 1 second, like this. So this is some measurement of power. And 1 joule per second is a watt. So this is 10 watts. A light bulb, a typical light bulb is something like 100 watts. So this gives you a rough idea of what power is. So 100 watts is that. So it's the rate of work at which you have some amount of energy here, how fast you're doing it. So if somebody is able to run up a set of stairs very quickly versus someone who runs up a set of stairs very slowly, they've both attained the same amount of potential energy when they go to the top of the stairs. But the one who goes up more quickly is the one who will have greater power because they're doing it with less time. So hopefully this is explained a little bit about the basic concepts of work, power, and energy. I hope this can help you for the upcoming exam.